Matthias. He was here a few years ago already. I don't remember the topic, but today I know it.
Neither do I.
Stage is yours. Thanks to have you back here.
Thank you very much for the introduction. So I will be talking about automating and managing an IoT fleet using Git. But first, a few words about me so that you understand also a bit the context. So already as a child, I preferred to automate things. So like a ball track, so I built an elevator so that I don't have to do this boring stuff by myself. So I built this elevator. Still nowadays, I'm dealing with elevators, but I'm not going to sell you an elevator today. So you will rather learn something about my open source project. So I wanted to learn something new, something more about software. So I decided to do my own open source project, and you will learn a bit about this today. And of course, during my spare time, I also have some other hobbies. I have a family, so I enjoy being out in the nature. So that's even more a reason to automate stuff, to be efficient, right? But first, I would like to start with a small exercise. Imagine you're the fleet manager of a huge fleet, huge IoT device fleet, maybe several 100,000 devices. And you got that job. You're trying to do your best and keep this fleet up and running. And what sometimes gives you sleepless nights, if you do something wrong, then the devices might go offline all around the world, and you have to go on site and fix each individual device. So, of course, there are some things to prevent this. You have a change advisory board. You discuss with some managers whether some changes should make it to production or not. But there are just the managers in this change advisory board, so you don't get into the gory details. Then you try with emails, you try to check what you really have to do. You, of course, also check the test reports that the development department is delivering. You even look into some Jira tickets, important Jira tickets, whether you missed something. Of course, with every release, you get huge release notes. Maybe there's something written where you should, for instance, not dispatch something to India. Then the developers drop some operating system images onto Artifactory. Usually I have the feeling, what do those guys do? Sometimes this is in, this works, sometimes that works. So honestly speaking, it's often a nightmare. Then on top of it, you get some individual Debian packages. You can also dispatch them then to the fleet. You never know whether they really match the operating system you just have dispatched. Then you're out of luck. You go to the coffee corner. Somebody tells you, keep in mind in Brazil, don't deploy right now to Brazil because there's something wrong with the MNO setup. But you go back to the desk, you have already forgotten this thing. You get a phone call, and crazy guy is calling you, hey, in China, did you take this in account? Please take this into account. Then you have some Confluence description, how you can dispatch a certain feature to somewhere. So you read the stuff there. You also, I'm not sure, does it really match the operating system image I'm currently deploying? You then try to discuss this on Teams with the guys that actually raise stuff. You have some Excel sheets, and finally, based on these Excel sheets, you go to your shiny device management solution, and you start to point and click and update your fleet. So, do you feel comfortable as a fleet manager? So I don't feel comfortable like that. So I try to come up with something that's hopefully a bit more comfortable, a bit more reproducible. So let's try to automate as much as possible. We can learn a lot from the IT, from Kubernetes, from those guys. We can learn a lot about automation. And let's tackle this stuff. So let's build tailor-made operating systems in a reproducible manner. Let's do some quality assurance in an automatic fashion. Let's do the configuration match. Let's do the fleet management properly. And hopefully the result should be high quality, reproducibility, security, reduced effort, and finally short response times. My speech is separated into 3 chapters. So the first chapter is about continuous integration. We build a generic operating system image from scratch. We dispatch it to a device and we automatically test it. Then the second part is about the device management. We want to turn this generic operating system image into a device that does something meaningful. So we apply an individual configuration to an individual device. And finally, we want to apply this to a whole fleet. So we want to have individual IoT devices out there that do exactly their use case. So let's first go with the continuous integration. So that's the manual step we have to do. First step, we tell GitHub what kind of operating system we would like to build. Then a job. So that's the cloud. The stuff down here is on site at my home. So the job goes down to a self-hosted Raspberry Pi GitHub runner. This GitHub runner pulls some repositories to the device. Then it knows how to build an operating system. And the operating system is composed of multiple Debian packages. So we fetch a bunch of Debian packages. We assemble all that stuff. And finally, we upload it to Mender, back to the cloud. And we tell Mender, hey, please deploy this operating system image to my IoT gateway down here. And that's not yet all. So we want to have it tested. So we run some tests on this device. And all the results get uploaded to GitHub again. So just this one manual step. We have a few important key principles. I will talk about security separately. But the whole thing shall be reproducible. Everything is automated. And also the quality assurance is automated. Let's dig into a few details. Let's try again. Up. Now it works. So that's how we start the job. In the first step, I tell, hey, I would like to have the Eddy Compulab project configuration repository. Let's take the master branch. This is the configuration we are going to take. And this UUID is the UUID of this device here. Of course, we want to have the whole stuff tested. And then we click Run Workflow, and then everything goes automatically. Then quite frequently, people think, okay, you're installing the operating system to a target system, you tweak it a bit, you rip it out of the device again, and that's then your golden image. No, sorry, I'm not doing that. So we start from scratch using dbootstrap. Then QEMU decides whether it needs some emulation. Let's say if I'm on an x86 architecture and I want to produce an ARM64 image, then I need, unfortunately, emulation, so it will slow things a bit down. But then we do a minimal root file system. Then with this root file system, I launch a container. Instead of a chroot, I take an LXD container, as I already was taking this anyway for other use cases. And once this container is started, I use Ansible to do a lot of customization, adding users tweaking SSH configuration, adding some packages, doing some systemd service tweaking, and so on. And finally, we have a fully configured container. We stop that container. We have then a root file system, and now some additional scripting converts this root file system into an operating system image that you can then DD to your device or whatever Android flasher tool, whatever. A very important aspect is the testing. And of course, I have limited spare time, so I don't want to reinvent the testing framework. So I'm using PyTest, as it is a very powerful testing framework. And on top of it, I'm using test infra. Test infra is from the server world. I treat this a bit like a server. And here are some test examples. Here I, for instance, check whether the disk got resized properly. And here I test whether the mount points are there. And one of my favorite tests is actually just asking systemd if all the services have started up properly. So this is one of my favorite tests. Another favorite test is to see whether, this is vital, whether time syncd was able to synchronize, and so on. So it's very easy to add tests. Then all the stuff I'm showing here is open source. So it's a bit difficult to hide some secrets in the source code. So you should probably not do that. So what I'm doing is that I store the stuff in action secrets. GitHub offers this possibility. On GitLab, I think you have HashiCorp Vault or something like that. So it's important to separate it. Good. And one remark about if you are running a self-hosted runner, that's something written in the documentation of GitHub. Don't connect to a public repository. It's not designed for this. So what I do is I have the private repository plus the same content in a public repository. So with regards to this, everything is available. OK, so now we have an individual operating system that is tested, customized for our use case, and it does not do something useful, as you can imagine. Let's now turn it into something useful. Again, the picture is very similar, and according to the eat your own dog food strategy, I'm trying to do a self-hosted GitHub action runner here with the strategy we have just shown before. So this time I don't interact with GitHub, I write the configuration to Mender. So this is the configuration I assign. Then a configuration artifact makes it down to the device. Then Ansible starts to run here. Respectively, first we take a playbook from GitHub. We clone some roles from GitHub. The roles will then fetch the C# binary from GitHub. So the runner is a C# binary. That was, yeah, OK. And on top of it, I need a few additional Debian packages so that I can use the tool EDI. EDI uses some additional tools, and they get installed down here. So we are finally ready, almost ready. So last step is that this runner tells GitHub, hey, I'm now here. You can use me. So the key principles here are idempotency. So if I tell the whole system again, hey, apply this configuration, I've done it before, nothing will change down here. The whole thing is traceable. So everything is stored somewhere. Then important, I don't try to reproduce APT in the cloud. So sometimes some people try to replicate the APT repository and tell exactly, hey, you need this version of and that version and this library and so on. APT knows about this, so I don't have to care about this. Important is also the security. Again, it's important that the whole thing is reproducible, so I can easily rip this device off, put another device here, change the UUID, and then I'm back with the self-hosted runner. And the whole thing is automated, so I just put the configuration here, and then I can go out and do some mountain biking. How does the playbook look like? The playbook is actually just 2 roles. The first role, I was even lazy enough to take this role directly from the internet, so somebody already had a role for the Ansible GitHub Action Runner. Cool. I wrote, of course, a role for my own tool, so that my tool gets installed, plus the additional packages I need. And once everything is done, we should have here the idle thing of this runner. So it should be displayed on GitHub. Hopla. A second use case, maybe you don't want to do it exactly like here, is to turn the stupid device, the stupid operating system we had, into a properly working kiosk terminal. Maybe you're not so happy if it asks you to do an upgrade to Microsoft Edge or some other message. So of course we are using also Linux here. And the process is more or less the same. So the only big difference is you add here another playbook. And you say which URL to display. But then the configuration is written to Mender. A config artifact makes it down to the Raspberry Pi. A small glue logic makes sure that the playbooks get fetched. Some roles get fetched, like the Ansible Galaxy approach. Then the playbook runs, installs some additional Debian packages, and automatically the system turns into a kiosk terminal. Okay, so now we have built an operating system, we have tested it, we have tweaked the setup. Yes, please?
Just a quick question. The Ansible is run inside the IoT device or from the outside?
That's a very good thing. So people keep claiming that Ansible is not good for IoT. And indeed, it's problematic. Let's say if you run it from the cloud and you do every command towards the IoT device with SSH. Then it tends to be slow, unreliable, because this IoT device might be switched off. So what I decided, and that's exactly what you said, I run Ansible here on the device. So it's powerful then, and it scales. But that's a very important step you have to make. Otherwise, if you try to run it from the backend, and let's say you have hundreds of thousands of devices, and Ansible is doing a thread for each and every device, you quickly run out of server resources. It's a kind of fire and forget. You put the job here, and then at some point the device fetches it. Okay, so let's go then to continuous delivery. So we just don't want to just manage one device. We want to manage a lot of devices. Here is a small demo fleet, and it is as it is in the real world. It's composed of multiple different devices. So here we have a kind of legacy device, a Raspberry Pi 2. Then we have this Compulab IoT gateway based on an IMX8 CPU. So it might be a Wi-Fi 6 hotspot. Then we have a Raspberry Pi 3, which is a kiosk terminal, another kiosk terminal. Then here this looks like a typical development board. It's a Variscite board. And then we have two Raspberry Pi 4. One you already know, that's the kiosk terminal. And the other one is the GitHub Action Runner. Actually, my boys want to turn it into a Minecraft server. Still have to negotiate. Okay, now, how can GitOps help? And those that were here yesterday know that GitOps is an auto-scaling fridge. and you can define the content of the fridge using a YAML file. And that's exactly what we want to do with the fleet. So we want to define the state of the fleet in Git, and then by some magic, it shall get applied to the fleet so that the target state becomes the actual state. And surprisingly, we cannot take the GitOps approach one-to-one for IoT. We need slightly different tools, so I would not claim it's GitOps. I would say it's inspired by Git. So what we try to do in the first step, we try to map our demo fleet to a Git repository. So the Git repository has several branches here. And we have the branch, the develop branch, where we do the work. And also, of course, some feature branches that are not depicted here. We do the work, and whenever we commit and we push it, it gets directly applied to the Variscite development board. Maybe it's on my desk, so if I break it, it's still okay. It's just me taking notice, so that's okay. But once we are happy and the Variscite development board is not broken, I can merge this stuff without changing anything. I can merge it to the main branch. And then maybe the kiosk terminal in the development building gets updated, so some other developers will then maybe let me know if something is broken. Still okay. Okay. But if it doesn't break, let's then merge it to the canary branch. The canary branch might be in the management building of your company. Again, the kiosk terminal. So if it breaks, you get some management attention. But still okay, you don't hit your customers. So then if the canary is still okay, you can merge it to the production branch, and it gets automatically applied to all the devices out there, maybe in batches. If you have several 100,000 devices, then you don't want to dispatch it all in one go. So it gets dispatched there. And hopefully, as you do not do changes up here anymore, hopefully nothing breaks out here because it has been tested. So let's take a look behind the scenes. How does it work here? So first, we do a change on a branch. We push it to GitHub, and GitHub sees the change, and then immediately a job gets dispatched to GitHub runner. This time we have the runner in the cloud. We don't have to do some fancy thing with hardware, so we are fine with the cloud. And I'm as a lazy guy. I also take Ansible here on the runner in order to orchestrate my fleet. So from Mender, which acts as the man in the middle, I fetch the facts of the fleet. So I get to know my whole fleet, and I know it then in the Ansible playbook. Depending on the target state and the actual state, I decide, okay, do I need an operating system update, or do I also need a configuration update? And I push it to Mender. Of course, here I can interact with SAP and whatever systems I have out there. I can collect all the information, make an educated guess how the fleet should look like. So then it's ending up here. And the device at that point in time might be offline because it might be some construction machine that is offline over the night. So it might already only pick it up the next day. So again, we have the important key principles of idempotency. If I apply the same configuration again, then nothing changes down here. I have a traceability. So all the changes on the fleet go into this Git repository. So not this bunch of input channels anymore. Then the rollouts are staged. So first, They are done on the develop branch, then on the main branch, and you can, instead of the CAB change advisory board meeting, you can do the sign-offs on GitHub. You can say, okay, this guy and this guy and this guy and these automatic tests have to approve, and then it can go to the main branch. You can also organize your playbook here in a way that you have staged rollouts, even on the production system. And from the main branch and upwards, there are no changes anymore. So between your develop and all the upper branches, you don't change anything anymore. And here, Mender is this important, could be something else, but it's the important man in the middle between the fleet and the management. So, already familiar tools take care of the orchestration. Here we have the GitHub Actions job, and the important part is down here. I run an Ansible playbook, and also here the action is already provided by someone else. That's the nice thing about open source, so I don't have to reinvent all the stuff. Then that's the Ansible playbook. Here that's just some checking, and the fancy stuff happens here. So I gather the fleet facts, that's the number 3. And I check then whether I'm on the correct branch, whether the subscribed branch of the device is equal to the applied branch where the commit has happened. I might install an operating system. So I have an AB update of the entire operating system if needed, and I apply the configuration. That's the inventory of the fleet. So basically it's just UUIDs of the individual devices I have out there. And this UUIDs are actually defined by Mender. So that each device is identified by a unique identifier. That was super fast, sorry. This here is an individual device configuration. So here I tell to which branch the device is subscribed. In this case, it's the main branch, not the production branch. And that's the configuration I apply. I say, okay, I have the template kiosk, so it shall be a kiosk terminal, and that's the URL that the kiosk terminal shall display. And this is the target state of the operating system image. So here I have the device type. For the Raspberry Pi, I dispatch this image. For the Raspberry Pi 3, I dispatch that image, and so on. It's clearly defined here, all in Git. And then 2 important remarks. So those that have now been observing the whole presentation will immediately see, okay, this is kind of a fire and forget approach. So you tell Mender to do something, but you don't check whether it has really done it. So the important monitoring aspect is out of scope of this presentation. This is a separate topic, and from my point of view, you can solve it on another layer. And it's absolutely required, but it's not part of this presentation. And then if you have a huge fleet, several 100,000 devices, you don't want to have a commit, a Git commit for each individual device. So what I would recommend there is that this Ansible playbook that is working in the GitHub runner shall then take this per device configuration from some database. But that is out of scope again from this presentation. So what's the conclusion about all this? So again, back to these different input channels. I guess we can reduce this to one Git repository where then everybody is talking talking the same language. I mean, we have seen it with the definition which device should get what software. You can also, of course, per device define that a certain device shall take another software, but it's clearly defined. So there is no question about it, which firmware the device will get. You have full traceability. All the changes on your fleet are tracked in Git. Then on the upper branches, you don't introduce any breaking changes anymore. So here we just have merge on main, canary, and production. Then the level of automation is very high. So human errors are almost reduced to zero. And we get staged rollouts. So even on the production branch, you can still tell the playbook to roll out in batches. But already here we have on the main branch some checks. We have on the canary branch some checks. And we can let it settle a bit, see whether it still works after a week, and then go forward. Then other key benefits. I would say it's a powerful toolbox. It scales. The stuff that is shown here scales, so it's designed for scaling. Then the components are all proven in use, and the components are exchangeable. So if you prefer Yocto over Debian, take Yocto. If you prefer GitLab over GitHub, take GitLab. If you prefer Subversion over Git, take Git. And the components are so far fun to work with. So I still enjoy, even I'm doing Ansible since years now, I still enjoy doing Ansible. It scales also, it's easy to understand. Yeah. As said already, all the stuff is open source. Here, that's the remark about this orchestration repository. So there is a public variant and a private variant. The private variant is just there because we need it for the GitHub Action Runner, but the content is the same. Then we have several repositories for the operating system set up. And we have some playbooks and roles to apply a certain configuration, and this is the repository that does the whole orchestration. There are a few links with some more description, and I guess we have 10 minutes for Q&A.
Thank you for the great presentation. I have one question regarding the canary deployment. So you have a separate branch for that. Does it then mean that you have kind of canary devices that you use all the time, where you say, okay, this is maybe less critical if this kiosk breaks down or something? Or do you really also rotate, kind of have different devices where you deploy the canary things first?
Yeah. So it depends on the use case. At Schindler, we also operate the alarm over the IoT devices. So I would be careful selecting the canary devices. But for instance, we could say, okay, the canary devices are located in each Schindler building all around the world. Then we also have the people that are aware of, okay, if the alarm is blinking, then I should tell someone. So it depends, but it's also a good strategy to have it randomized. It's not so good about traceability, so we need to somehow keep it under control, how much traceability. Yeah. But there are different strategies for selecting the canary. So if you offload the subscribed branch to a database, you can do the randomization.
Okay, but that means like also with an operator, like a blue-collar guy from Schindler somewhere, he knows, okay, that's my canary device, so if the alarm goes off on this device, maybe that's something related to the latest change or something.
That's absolutely possible, and then hopefully there is some awareness within Schindler to call the developers.
Awesome, thanks.
Yeah.
Thank you. I was asking myself, because you seem to have pieced together quite a lot of things that are essentially already built into Puppet. And I operate not a big fleet, but maybe a reason to not use Puppet.
Honestly speaking, I was already using Ansible to customize the operating system image, and it was a good match there because you don't have to install anything on the target device. And that was kind of a deal maker. And then I said, okay, that's great. I can also use it like that on the fleet, but I have to do it on each individual device. But there are good reasons also to use SaltStack or Chef or Puppet. So that's absolutely doable. I mean, I did this during my spare time, so I didn't have the time to yet take another system. So I have to be a bit lazy about it and reduce the number of tools that I need.
Maybe a follow-up to that. Have you thought about using Docker to build the operating system and then deploy it like this?
So what would be a possibility that we deploy Docker containers to a minimal operating system? That would be one possibility. Actually, I'm taking on purpose LXD because I want to run kind of a digital twin of the operating system on my host system so that I have an efficient development workflow. And there I was not using Docker because I want to use a container that is close to a real operating system. And on LXD I can boot the whole systemd stuff, multiple services. So I'm very close actually to the real operating system. And that was the reason actually to use Docker, not to use Docker, but LXD in my case. But if I would do the decision again today, I might also use Podman, because Podman also supports starting systemd. I guess also Docker does it by now, I don't know. Didn't follow up on this.
Okay, thanks.
Thank you.
Maybe a question about the stability of this system. I mean, for us, it's very important to have firmware updates deployed in a very atomic way. Also, clouds are doing a huge effort to go to more and more atomic deployments so that your system is never in a transition, undefined state. Some parts of the configuration are already on the new state, some are in the old state, and so on. So this looks like this can happen very easily with that system.
Yeah, let's say it like this. So we have the part of the operating system update where we have an AB update. And honestly speaking, the configuration changes, I would like to keep those minimal. So the problem we have at Schindler is that we have a huge diversity out there. So we have very old and brand new elevators out there. They have different communication channels, and you have to do a minimal number of changes there. Maybe you have to enable some remote APIs and so on. So the whole big thing comes as a big update. And this also makes the management a lot easier. Of course, we also have the discussion about Delta updates. That's also an important discussion. But depending on how your setup is and how your technical operations centers look like, it's even more difficult to explain than what a Delta update is. So if you have just one big pop that you push out, then it's way easier to manage over time. But Delta updates would be nice, as atomic, as you said, as possible. Yeah. Also for testing, atomic updates and downgrades are extremely helpful because then you can test a certain use case. And atomically go back to the previous use case by just rebooting the device. So that's really nice, and it's for sure a good idea.
Thank you.
Hi, I have a follow-up question regarding the what is exactly in the Git or you mentioned that you have a file. You mentioned that you have a file where all the devices are listed. Is that right? Or so 100,000 a file with 100,000 lines, or even more?
Yeah, this in the real world scenario. This is just for my demo project. In the real world scenario, we would offload this per device configuration and the devices into a separate database. I mean, this doesn't scale if you have 100,000 commits on this fleet management repository. Then it's very hard to get the real changes out of the repository, and a device in most added or not.
Okay, then thank you very much, Matthias, for the presentation.
Dankeschön.